In this chapter, we're going to look at carbonyl condensations. If you recall, we've already looked at some condensation reactions. Condensation is when you join two molecules by the removal of another. So, for instance, we've seen that esters can be made by condensing an acid and an alcohol. By the removal of water, we condense them together into an ester. When you have two alcohols, you can condense them by the removal of water to make an ether. So now we're going to look and see how can we join two carbonyl compounds by the removal of another compound, for instance, an alcohol or water. Remember that the alpha hydrogen on carbonyls are acidic, and ketones and aldehydes, they require strong hindered bases to completely deprotonate. We use LDA. You can use something like sodium amide or sodium hydride, but this is hindered, and sometimes you can have nucleophilic, not hindered, and sometimes you can have something happen besides deprotonation because it can be nucleophilic. But LDA cannot be nucleophilic, so that's the best one to use. If I look at a diester, a dicarbonyl, where you have a proton that is alpha to two carbonyls, we can completely deprotonate with sodium ethoxide. If we go with something less basic than sodium ethoxide, or with ketones and aldehydes, if we use something less basic than LDA, what happens? We get equilibrium concentrations, not only of the enolate, but we also will have some diester or some ketone and aldehyde remaining behind. If you do not have complete deprotonation, the carbonyls that are left behind are subject to nucleophilic attack. So if you have enolate present and ketone or aldehyde present, what happens? The enolate can be nucleophilic and attack the carbonyl. The enolate can attack the nucleophile, and once you attack the nucleophile, you've got this negative charge on the oxygen that if water is around or anything that's protic, it can protonate it, and then we have what we call a ketol or an aldol. If this were an aldehyde here, we would call it an aldol. If it's a ketone here, we call it ketol. This is formed at equilibrium. If you notice in the previous slide, everything was double arrows. So we are having the equilibrium formation of an aldol or a ketol. For some aldehydes, the adduct is favored, and so you have aldol, the aldol form. For some ketones, you can form it, but for the majority of ketones, you're going to have the ketone side favored, and the adduct won't be made except for in tiny concentrations. And even for most aldehydes, you have very little of the aldol being formed. But if we heat and remove water, notice what happens. We have water can be removed here, and it forms a conjugated carbonyl, which is very stable. So if we heat and remove water, we can force the equilibrium to completion by forming the unsaturated carbonyl. This is called an aldol condensation, and it's aldol because we first saw it most easily occur with aldehydes, but it occurs with ketones too. This is base catalyzed. Sodium hydroxide is adequate because all you need to do is make a tiny amount of the enolate. And then dehydration forces the equilibrium to completion. Let's look at it. Here is acetal. Here's another acetal. What's going to happen is the sodium hydroxide will remove a tiny percentage of protons from one of the aldehydes, from some of the aldehydes. That will do nucleophilic attack, and then we make this all. Notice, we're going to go through the mechanism, but this carbon basically is attached to this carbon now. Y'all see that? And this alcohol group was from this carbonyl. It's just this proton came off, this did nucleophilic attack, and then the proton protonated the hydroxyl, the alkoxide. Okay, once we form the aldol or a ketol, we can force this to go to completion by the removal of water. So here you see the ene formed by the removal of water here. So you go ahead and try to figure out what is the product of the aldol condensation of propanol. So draw 2-propanol, and see what you can do about condensing them together in the aldol condensation at the alpha carbon. Okay, the first thing you want to do is draw two propanals. So here's one and here's the other. Now, the easy way to do this is to do it visually. Chop off one of the oxygens. Now that you have that chopped off, that's going to be the ene that forms between the carbonyl carbon and the alpha carbon. So you just tack them together now. Do you see how easy that is? Aldol condensation products are really very easy, whether they're aldehydes or ketones. Just remember, what are the conditions? You have to have a catalytic amount of sodium hydroxide, and you need to remove water. You have to have a base that does not completely deprotonate the carbon, alpha carbon, because you have to have equal concentrations of both the enolate and the carbonyl. Okay, we've got another one for you to try. Go ahead and determine what is the product of the aldol condensation reaction of cyclohexanone. So now if you did it visually, you know you draw 2 cyclohexanones and then you tack them together at the alpha carbon. So you should have this as your product. If you have a mixture of carbonyl compounds, usually what you have is a mess. You can have, let's say you have carbonyl compound A and B. You can get A and A doing an aldol condensation. You can get B and B doing an aldol condensation. And you can get A and B doing an aldol condensation where B is a nucleophile. And then you can get A and B doing an aldol condensation where A is a nucleophile. And so you'd have 4 different products. Whew, what a mess. But you do a mixed aldol condensation when you have one of the carbonyls does not have an alpha hydrogen, and you get one product forming, because this accumulates with time, and you can't have this won't reverse. Once you form this, it does not, the equilibrium does not go backwards. The others can all go backwards as they form, and so this one will accumulate. So let's go ahead and look at this example. Why does this work? Well, this has alpha hydrogens, but you see there's no alpha hydrogen here, so we get one product. So go ahead and draw the outcome of the aldol condensation of benzaldehyde and cyclohexanone. One of them does not have alpha carbons. Figure it out. Okay, this is benzaldehyde and this is cyclohexanone, and what we're going to do is figure out the aldol condensation. You can see there are alpha hydrogens here and here, but there's no alpha hydrogen here. So let's go ahead and figure out what will be the aldol condensation. Because this is the one that does not have alpha carbons, it cannot be the nucleophile. This must be the nucleophile. So this is the oxygen that's going to be lost in dehydration. So you tack it onto the alpha carbon of the cyclohexanone and you end up getting that product. Okay, you can also do a mixed aldol if you have one more acidic than the other. Now, till now, we've been talking about equilibrium concentrations rather than complete deprotonation. But if you want the aldol condensation to go with two different ones and one is significantly more acidic than the other, what you can do is choose the one that you want to be the nucleophile and make it be the nucleophile by deprotonating it only. So let's look and see what I'm trying to explain to you. This right here is more acidic than this. This is the di-carbonyl compound is completely deprotonated by sodium ethoxide, and there would be only equilibrium concentrations of this. If we add one equivalent of this is going to be doing nucleophilic attack on that because this is the only nucleophile that would form. Once that nucleophile forms, then you can remove water and you get the aldol condensation product. So you can see, chop off this oxygen because that was the one that was undergoing nucleophilic attack, and you lose water to form this aldol condensation product. And then we can do other things with this that would be kind of cool. Here we can treat with acid and decarboxylate, and then you would have the ketene. You can add things 1,4 to this conjugated carbonyl, like an amine or something else that's not basic, not very basic. And so you can see that this gives us a lot of opportunities for further reactions. Here's an example of an aldol condensation that forms a ring. Rings are very favorable reactions. So if a ring can be formed, it usually is. And 1,4-diones and 1,5-diones will do an aldol condensation quite easily and selectively for the ring form product. You don't get mixed aldol, a bunch of different products. So if I look at this, 1, 2, 3, 4, 5, well, how is the aldol condensation going to form? Okay, what's going to be doing the nucleophilic attack? You're not going to form anything but 5- and 6-membered rings. Other size rings are not favored for formation. Thermodynamically, they're not as stable, so they don't favor formation. So I can deprotonate here, here, and here. What ring sizes would I get? Well, if I deprotonate here and attack this carbonyl, I would have 1, 2, 3, 4 membered ring. Not very good. If I deprotonate here and have nucleophilic attack here, how many atoms would you have in the ring? 1, 2, 3, 4. If I deprotonate here and do nucleophilic attack here, how many atoms would be in the ring? 1, 2, 3, 4, 5, 6. So that would be highly favored. So if I deprotonate here, that means I'm going to be losing alcohol from this carbon. So this is going to be gone. So I chop that off and tack it on over here. And you can see that's the product that I have there. This is this carbon. This is that carbon. Then you have 1, 2, 3. And there's 1, 2, 3. And then this is the carbon that's right here in this double bond. You see how chop that off, put an oxygen there, and make that a methyl group? You have this back. So now you try to determine what is the product of the internal aldol condensation of 2,7-octadione. Well, here is octadione. And what is the product that's going to form? We go through and count. 1, 2, 3, 4, 5, 6, 7. That'd be no good. 1, 2, 3, 4, 5. That's good. A 5-membered ring. So I'm going to make this and this join together. And I get that. And it's just going to require doing practice of these problems. So sit down and do a lot of problems.